give me $20 in the USA. Okay. Sorry for the delay getting ready. A little bit of trouble with the sound. Yeah, we're going to continue talking about the basics of motion. We're going to get into Sir Isaac Newton's laws of motion by the end of today. And but before we do that, I want to review what we did last time for a little bit of extra emphasis. And we're actually going to extend it a little bit. We reviewed distance polygons, which for an object in constant velocity is a rectangle. For something with constant acceleration, it's a polygon. It's a triangle, a right triangle. If you're speeding up from rest, it's particularly easy. If you're slowing down to rest, it's also fairly easy to interpret. But we did some fancy ones yesterday. And we talked about a refinement of the distance polygon concept to an object with a changing acceleration, for which my example was a rocket on takeoff, which is losing mass and therefore increasing its acceleration. So for every cubic meter, or for every pound of rocket fuel, every kilogram of rocket fuel that it oxidizes in the motor, it gets so much thrust. But as it does that, the same amount of thrust, but it's working on a rocket that's lighter and lighter and lighter, because it's every kilogram that it does that, it gets thrust, but then it loses that kilogram out the tailpipe. So, and we compared it to this particular, there we go, this particular shape. We talked about a velocity graph that was curving gradually steeper and steeper. By the way, show of hands, please, if you used, Darian, can you go see if those students are in the last 3 rows over there? If they are, you can bust them. Don't look behind you. Yeah, get those rows. We're going to really need to follow that procedure of forward positioning on exams. Show of hands, please. If you looked at the talking PDF in web courses, raise your hands high so I could. Oh, not many of you. All right, well, it's up to you what you want to do. Of course, if I ask you a question for which the answer is encoded in the talking PDF, if you haven't looked at it, you're going to be toast. But that's all right. You can certainly do that. And we mentioned that the famous movie Hidden Figures, which is really good. That was your homework assignment, to either look at it or figure out how you can get the DVD or something for it. It's, it'll keep the whole semester. You can keep thinking about that. Here's the image that we actually looked at. The crescent up there between the actual curved line and the trapezoid upper surface, the hypotenuse of a right triangle. We talked about that at length, so let's review that. That slivery crescent from yesterday represents the amount of overestimation that using a trapezoid gives you. So a trapezoid is easy, all right? And here's the trapezoid. It's an overestimate. The trapezoid that we did yesterday, or Tuesday, all right? It's fairly easy to do, but it does overestimate relative to the true distance. And that crescent, here's the crescent, and let me just park it over here to the side, and then let me put the overestimate over here to the left. That overestimate is useful, but it does overestimate by the area of that little slivery crescent. Here's the true. This yellow area here, let me park it over here to the left, or to the right, I should say. That's the true area. And you know, this overestimate, the pink rectangle topped by a blue triangle together is called a trapezoid. That's a pretty good estimate. It's not like, you know, wildly inaccurate. And the narrower we make the delta t base, the more accurate that trapezoid becomes. But another thing you can do is you compensate for that overestimation by making a polygon that underestimates. So that would be like this one. Now take a look at this. I want you to look at it carefully. All right, here's my, in the middle, that's the sketch, or that's a slice of the talking PDF from Tuesday. All right, and we have to the left, we have the overestimate, and we have in yellow the true distance. And then here's one that you could use. Basically, that's taking the same blue triangle, shifting it downward, and then making the pink rectangle a little bit shorter. All right? Now, that one is going to underestimate. So what you could do is you take your overestimate, you take your underestimate, and then divide by, you know, add them up and divide by 2. And that, you know, that would be even more accurate. So that is a strategy that you can do no matter how you're calculating it. Now, the National Aeronautical Council, NACA, which was in existence before World War II, became huge in World War II and persisted into the late 50s when it was replaced by NASA, the National Aeronautical and Space Administration. Up into the late 50s, early 60s, they were using a lot of humans to do that computation. You know, construct the trapezoids, compute them, and then construct some more trapezoids, compute those. And it's just 1/2 base times height plus a rectangle, so it's not a great, but they got to do zillions of them, and they can't make an error. All right, and you have to do it in an organized manner. So it's actually a difficult problem. So, and I mentioned how Dorothy Vaughan and all those guys in that movie and many others, if you read the book, it's really, really interesting. The things that they went through, I mean, the discrimination they went through, and through which they prevailed, it's really inspiring. Plus the fact that they're all scientists and mathematicians, it's pretty good. Now, eventually, IBM started producing the big, you know, silicon-based computers for NASA, and so NASA started using the machines. The very first computer of that kind actually ran with something called tubes, vacuum tubes, which I can just barely remember from when I was a little shrimpy kid. You could still find devices with tubes in them because it's a good technology, but it's not very sturdy. You couldn't build much of a rocket with tubes because they're made of glass. They're like, in a lot of ways, they're like a light bulb, but then so they're made of glass in a vacuum. You got to keep the vacuum. You got metal plates and the electrons are accelerating and stuff. And you use these tubes and you can build a computer that would easily fill this room to get like 1/10 of the computing power that you have in a cell phone 15 years ago or longer. So they first had those, and they developed those in World War II. You know what they were using them for? To break German and Japanese codes. That's where the high tech is, and it always is. You know, the code breakers need lots of computer power as much as they could possibly get, and so their technology is always the best. But eventually NASA started getting them, and so they started using the machines. And guess who was in charge of the machines? Yup, Dorothy Vaughan and the rest of her group. They learned how to run the machines. So she was still the BOSS. It's a wonderful story, so I encourage you to get that. And let's continue talking about, oh boy, I have all these diagrams in the background. I forgot to take those out. That's all right. Let's do some iClicker questions. And so get your clicker out. And if this is your first, wait a minute, don't close that. If this is your first time using it, press the power button and hold it until the letters flash in the upper left, and then type in DD, and you'll get the Go Nitro message, and then ready, and then you'll be ready to click. All right, now you can go back to the regular laptop display. All right, so here's your question. And I want you to think about this carefully. You know, when you're good, don't just take a good seat. Everything's good. If you're late for class, just come on in. Don't be late for exams, though. But lecture, it's not a big disaster. Sneaking into the front row when you're late. Think very carefully. Read carefully and think. Positive acceleration along the x-axis. There's an example of an x-axis measured in meters. And that is a really small car. If you look at it, to this scale, it's less than a meter in length. So actually that would be like a little toy car. So if you have a Kia, if you're bombing around in a Kia, it's a little bit bigger than that if it were drawn to scale. Anyways, go ahead and think about what you're doing. And remember, in class, in lecture, you can talk to your neighbors about the question and kind of, if you're sitting next to somebody, if you're sitting by yourself, you can't talk to anybody. Or you could talk to somebody behind you or somebody in front of you. But definitely, I encourage you to interact with your neighbor if you have a neighbor to interact with. And just talk it over. All right, what do we got for participation here? Okay, 100. Good. Actually, I should have told you to make this a multiple short answer so that we can select more than one correct. All right, 20 seconds to vote. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And most of you have voted for that. All right. A lot of you voted for that. And actually, that is a good answer. Oh, wait a minute now. This is also a good answer. Ooh, you know how many people voted for this? 4. If you voted for this, you still didn't get the best answer. The best answer is actually both A and B. And you know what? Most of you did choose that. But I'm going to ask Darian to see if she can convert this into a multiple correct answer type question. And you can, hold on a second. You can just do what you can. You won't be able to, no, you won't be able to do that.
Okay.
You might be able to do it in
Post.
the grade book.
Okay.
So, all right. So fool around in this and get this up to L6 and stuff. So if you're moving if you have a rightward acceleration, that means either you're gaining speed to the right or you're losing speed if you are going to the left. So both A and B are the best answer here. Now, if you answered A, we're in the middle of trying to get you to have points for this, all right? For all three, A, B, and C. Now, it is similar for free fall. So make a note, Dr. B's next topic after that question. Oh, wait a minute, did I say that question was a topic? Yes. Whenever I'm giving you a multiple choice, a iClicker question, calculation, anything, it's usually to get you to think and therefore talk about a particular topic of interest. All right, so the meaning of acceleration is of interest to us. The question was about horizontal acceleration. Same thing holds for free fall. So here's a bunch of supposedly rational people jumping out of a perfectly good airplane into the wide open sky in free fall, and eventually, hopefully, their parachute will open and they'll land safely. But on the way down, the y component of the velocity is negative. So make a note of that. Soldiers jumping out of an airplane. On the way down, the y component of their velocity is negatory. All right? In other words, they're moving downward. Right? So on the y-axis, the vertical axis, that would mean they're heading downward. They're falling. Right? And as they fall, for every second of free fall, they're gaining speed until they pop the chute or until they hit terminal velocity. And that's a little bit trickier of a concept, but for the first few seconds anyways, they're gaining a lot of speed. They're really going. Raise your hand if you've ever parachuted out of a plane. Anybody here? Oh my goodness. That's two people that are very brave. I would be pretty nervous to do it. But on the way down, you're gaining downward speed. Your velocity is negative, and you're gaining more downward speed. All right, second part. And now this is considered a free fall trajectory as well. Once you hit that golf ball, on the way up, the vertical component of the motion is positive. Vy is positive. You're moving upwards along the y-axis, but you're losing. So this means that acceleration due to gravity, whether you're going up or going down, that acceleration is going to be a negative number of meter per second per second. Acceleration is meters per second, so much speed for every second of free fall, or more abbreviated form, meters per second squared. And gravity is going to have a negative number. Now, in the British system, the feet, inches, and so forth, yards, you'll get a negative number. In the metric system, you'll get a negative number, okay, in free fall. So whether it's a ballistic trajectory like this, or just jumping out of an airplane, or you dropping a water balloon off the top of the library, when you see one of your friends going by underneath, anything like that, gravity's going to be a negative number. It's going to be downward. The acceleration due to gravity is going to be a negative number, and we're going to study that today. Because we're going to talk about Galileo's use of free fall as the prototype of all accelerated motions. So Galileo, he didn't really know anything about rockets, but he knew that Freefall, dropping something off the side of the Leaning Tower of Pisa, was fairly simple. He understood it fairly well. But he knew that there were other accelerated systems than that. Now, let's take a look at this speeding up. And this is a distance polygon here. You got a trapezoid. The velocity graph for something that's speeding up as it goes to the whatever direction this is. I didn't really say Vx or Vy, but it's speeding up. Okay. And so the area under that red line is the distance traveled during the time interval between the two dashed lines. So Ti to Tf. Okay, that's this. All right, so that's the total area that you move. It's going to be a gain, so it's going further to the right if it's an x component of the velocity. And you can break that apart, as we have already done, into a right triangle and a rectangle. Here they are. And the reason I want to bring this up to you is because we're going to start putting together an equation that encodes the accelerated motion in free fall. All right, and it's going to be but it's based on distance triangle and distance rectangle concepts. Now, for this object, it's two rectangles. I have a 1/2 AT squared triangle for the first polygon, and I just have a VT rectangle. It should really be VI, because that's the height up here. Let me get my cursor. Here's the height at the start. Okay, and here's VF where it finishes. All right. So VI is here, and that is the height of the rectangle that's hidden inside this polygon. So really, the amount of distance that you acquire, you can put these two polygon formulas together. Here's what it looks like. The change in the x-coordinate, if this is the x-axis motion, VIT, that's the distance rectangle, plus a little bit of distance triangle action, 1/2 AT squared. All right, now, so this is getting to be a little bit fancy. All right, and we're going to be applying this concept today to free fall. Okay, and VIT times 1/2 AT squared. Now, those of you that have had calculus, you may recognize something here. You may recognize derivatives and integrals. And yeah, that's definitely happening here. But for us, we can just, for us that we're not thinking about calculus, let's just think about distance triangle and distance rectangle. That's perfectly fine. All right. And here's my note to you from chapter 2-2. Galileo chose free fall as the simplest acceleration to study. And it's definitely useful for any acceleration because any, like the curved velocity graph, you can break that down. And basically what you do with the trapezoid strategy is you think of each little sliver of the motion not as a curved surface on top, but as a triangular surface. And if it's triangular, that means constant acceleration. So free fall is a good prototype for all accelerating systems, even something complicated like rocket flight. Now here's what Galileo wrote about accelerated motion. He wrote that I observe a stone initially at rest falling from an elevated position and continually acquiring new increments of speed. All right, so that means that on the way down, it's more increments of speed. It's getting faster and faster. So now he didn't have a radar gun and he didn't have a speedometer on that object that he drops from rest from an elevated position. But if he did, he would see something else. And that is another part of this quote. If now we examine the matter carefully, in other words, make careful measurements and observations, we find no addition or increment more simple than that which repeats itself always in the same manner. All right, so what that means in free fall is this. He'll drop it from rest and start a stopwatch. So at time t equals 0, it's at rest. So its speed is 0.0. And if he had been working in the metric system, which wasn't invented for another couple hundred years or so, it would have been, after 1 second, 9.8 meters per second of downward speed. Today, we would measure it that way. You know, if you have a radar gun, you drop a water balloon off the top of the library, and you use a radar gun like the police, and you get the speeds every second. First one's going to be 9.8 meters per second. After another second, 19.6. Every second, it adds another 9.8. And that's what he means. That the increment is, it always repeats itself in the same manner. That is constant acceleration. And for free fall, it's 9.8 meters per second of downward speed for every second of free fall. Now, in real life, there's a little bit of air resistance. But for simple systems that aren't going too fast, just straight equal increments, 9.8, 9.8, 9.8, 9.8. Every second of free fall works perfectly fine. All right, so just put etc. and make a note that the direction is downward. Okay, and that's this idea that the increase in downward speed is always the same. And that's for free fall. Now, the increase in the upward speed for that rocket is not always the same, because that velocity graph is getting steeper as time goes on. But for free fall, downward speed, always another 9.8 meters per second of downward speed for every second of free fall. And that's one of the key ideas that Galileo studied and verified and published his theory about, and it is incredibly important. And fellas, okay, if I can hear you up here and you're distracting me, then it's possible that people that are working their you-know-what off to get good grades in this class behind you or near you are being distracted as well. So now if you don't want to, if you don't care about your grade, that's one thing. You can take off. But if if you're distracting somebody else, I don't like that. And I don't like being distracted myself. So try not to talk over the top of me. Because this room, I can hear, if anybody's talking, I can hear it. All right? Even if I can't make out your words. All right, so free fall. So when you're, and here's the other thing that you want to think about. In a ballistic arc, like the golf ball on the way up and on the way down. On the way up, it's losing. Make a note to yourself. Now, this is just dropping it straight down, easy. But a ballistic arc of a golf ball on the way up, it's losing 9.8 meters per second. If it's got anything upward, it loses 9.8 meters per second of it every second on the way up, until it doesn't have any upward speed at all. And then it starts accelerating down. It starts moving downward. It starts to drop. It gets to the top of the arc when all the velocity is taken away by gravity. And then after that point in time, it starts arcing back downward because gravity is giving it downward velocity. All right, so free fall and acceleration. Free fall acceleration on the surface of the Earth, it's approximately 9.8 a meter per second, or 9.8 meters per second squared. And go ahead and make a side note to yourself. This is true also at the top of Mount Everest. You know, it's a little bit further away from the center of the Earth. So gravity's a little bit weaker, but it's still pretty close up there at the top of Mount Everest. Still pretty close to 9.8. If you go down to the bottom of the Mariana Trench in the Pacific, the deepest part of the ocean, it's still pretty close to 9.8. So 9.8 is good everywhere that we humans have gone on the surface of the Earth, whether it's the bottom of the deep part of the Pacific or the top of Mount Everest. Now, if you're in a space flight, you know, so if you're up there in the space shuttle or the space station or something, gravity's a little bit weaker up there. So your acceleration due to gravity up there, you'll still, you know, you can still drop stuff out of the space shuttle, but it won't accelerate at 9.8 meters per second until it gets a little bit closer to the surface of the Earth. It'll be a little bit weaker up there. So remember, delta V over delta T is the basic definition of acceleration, and you can see it here. That's how we define an acceleration. All right, drop distance. We've already talked about distance triangles. Here's a velocity graph. Go ahead and draw this one. This is you dropping something from the top of, oh, you know what? We have another question. We're going to have a calculation for you here in just a second. This is you dropping something from the top of the library, okay? Actually, it's from the top of a pretty big building. But it starts at 0 here. This is you letting go. And then after here's 5 seconds out here. So here's 4, 3, 2, and 1. So at 1 second, your velocity is negative 9.8 meters per second. So it starts at rest up here. You drop it from the top of the Leaning Tower of Pisa. And after a second, downward, negative 9.8 meters per second. Right? And then here's another second of free fall. And no air resistance, just straight free fall, negative 19.6. Add another negative 9.8. You get negative 29.4 after 3 seconds. After 4 seconds, you've acquired another 9.8, total of negative 39.2 meter per second of downward speed. So at this point, 39 times 2.24 is about 90 miles an hour maybe. 80-something, 90 miles an hour, so it's really starting to go fast. All right, and here's the distance. Go ahead and construct your distance rectangle. This one's below the x-axis, so it's actually a drop. Okay, and so you would compute this as a negative, whatever it happens. Actually, let's figure that out. 1/2 base times height. The height is negative 39.2. And the base is 4 seconds. So 4 times 39.2, actually 1/2 times 4 is 2 seconds, times 39.2 negative. So that's negative, anybody verify me, negative 78.4? Okay. And so that means you've fallen 78.4 meters. That's a pretty tall building. I don't think we have anything that tall in Orlando. But, yeah, that's what it would be. And this vertical side here is G delta T. G is the symbol that we customarily use for the acceleration due to gravity on the surface. I mean, we use it all the time. It doesn't have to have its own symbol, but it's acquired its own symbol, little g, for the acceleration due to gravity at the surface of the Earth. And here's the base. Here's the basic formula. If you don't really care, if you know that it's starting at some point and you just want to know the total distance, you know, as a tape measure, you just go 1/2 GT squared and use positive 9.8. But if you're trying to figure out velocity components, you're trying to figure out positions in a coordinate system, you got to use negatives. And we'll do that in a second. So the drop distance formula, that's what I call this. the drop distance formula, 1/2 gt squared. Yeah, it's, distance, let's see. Delta t is 4, so t squared is 4 squared. 16 times 9.8 times 1. Okay, so 16 times, what's 1/2 times 9.8? 4.9. So 16 times 4.9, so that's about 70 something, 80. Okay, so this is good. All right. Now we're going to do an example from the Lord of the Rings, from the Mines of Moria. And this is Pippin, right? A fool of a took. This is the famous scene where he drops something and he wakes up all the orcs like a nitwit. So here's your, hit the refresh key on your calculator, or excuse me, the refresh key on your iClicker. All right, how deep is the well? You drop a rock down a well, you hear the splash 3.2 seconds later, how deep is it? 4 seconds, it's going to be 78.4. We already figured that out. All right, now let's figure this one out, 3.2. So you can use 1/2 gt squared. Okay, 1/2, 9.8, and then 3.2 quantity squared. All right. Now you're going to have numbers here, and you start with a 0. So type in the whole number part of your answer, and then maybe 2 digits of whole numbers if you want, and then a decimal point. Give it to me to the nearest 0.01 meter of drop distance. So that's the nearest centimeter, actually. So 0.01 meters. So, and talk to your neighbor, coordinate. And if you're using your cell phone now, my word of warning to you is the following: that on exam 1, you are not allowed to use the cell phone. You have to use a regular calculator. But in class today, go ahead and use it. And if you don't have a cell phone calculator, just do it on pencil and paper. 5th grade style. You can do it. 3.2 times 3.2. It's going to be, I don't know, what is that, 10, about 10 or something like that. Times 9.8, divide by 2, ding. So my estimate is should be about 50. Anybody coming in at about 50 or something? Should be about, yeah, it's a clicker. Yes, dude, yes. Hit the refresh key. Do not miss, especially if you got here late, do not miss the clicker question. Yeah, Kadia. No, what I do is, the formula is 1/2 gt squared. So that's 1/2 times 9.8 times whatever t is, quantity squared. So the first two, Kadia, are 1/2 g. So when I'm doing it on the calculator, you know what I do? Instead of typing in 0.5 and then 9.8, I just type in 4.9. Because that's half of 9.8, right? So I do 4.9, and then I do the square. So then I do, 3.2 quantity squared. That's got to be close. Make sure you double check your answer and round off carefully. Looks like we got. All right, now if you typed in a negative number, don't type. We're just looking for how deep is the well. All right, a negative number would be good if I wanted the coordinate, the y coordinate. But we're just talking about how deep the well is, so just type in the number and make it a positive number. So if you have a negative something, point something, something, change that over to a positive. And you guys are all looking pretty good here, actually. Oh, you know what? Did you figure out a way to change that problem? You did? Nice. I'm gonna have to, you have to show me how to do that. All right, 137. Okay, 30 seconds. Uh-oh, I see somebody that typed in a gigantic number. They forgot their decimal point. And turn the lights all the way up. I apologize for the decimal. Well, the decimal point, I wish it were bigger, but it's very hard to see, especially if the room is dark. All right, so take a minute to double check. There's 4 of you that obviously forgot the the decimal point. But actually, this is instructive, so. All right, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2. One. Anybody still need time? Hurry up. And don't forget to hit the send key. Got it? 0. Ding. All right, go to this display. Let's look at it. And do the lights. Now, I want to show you this. The actual answer is 50.18. So most of you got that. Darren, you can mark that one green. Okay. Now, 50.23, we're not going to mark green. 50.17, we're not going to mark green. It's not rounded off properly. Negative 50.17, we're not going to mark green. 50.12, whoa. Dare, can you scroll down and let's look at 50.12, I don't know how you got that. Now 50.2 is nice if I ask you to round off to tenths. All right, 2 of you voted for that. 50.2, whoa. That one, I'm not really sure how that one got in there. 50.21, 50.7, no, is that the, let's go and look at some more.
There we go.
Negative 50.12, 5, 5.18. Okay, if I see that 5.18, that tells me that somebody missed the 0 or something. 6.7, I don't know about that one. 15.68, let's go and look at some more of them. 15.7, 50.07, 50.1. All right, now look at that, 50.176. There's somebody that didn't round off enough. All right, 50 point. Now, here's the person I was looking at. There were 4 people, but one of you didn't hear what I said or didn't pay attention. 5,118. That's a student that messed up the decimal point. All right. Now, I'm going over this with you right now for a particular reason. Question?
For 50.23, right? I got that because I've been like conditioned to put 9.81.
Yeah, okay. Yeah.
Still not getting
We're going to use 9.8, but I'm about to tell you how I handle these small little variations. So what I do on an exam, here in class you can see that we're clicking on answers and calling them correct. On an exam, I look at it in a spreadsheet, and on an exam, what is your name again? Dior? Dior, on an exam, I would look at that, and on an exam, if we did an I-clicker question like this, it might be 2 or 3 points. So instead of giving 3 points, I might give 2 points, partial credit. So this guy down here at 5,018, I would look at that and I would have pity on him and realize, knowing that the decimal point is pretty nasty, hard to see, I would give him, like maybe 1 point partial credit or 2 points partial, something. Because it's obviously they knew what they were doing, but they kind of messed things up a little bit. All right? So just remember that for the exam. Go back to the display. So here's the calculation. If you messed up, here's how it goes. 0.5 times 9.8 meters per second squared, and then here's my 3.2 drop time seconds squared. All right. Now, as I was telling Katie up here in the front, my normal thing is to streamline things a little bit. So the first two parentheses, I just combine those together and call it 4.9 meters per second squared. And then over here, 3.2, I square that out and I get 10.24 seconds squared. Question? Because, as I mentioned, if you know that it's just a drop distance and all you want to know is how deep it is, not its coordinate. I mean, if we were doing X and Y coordinates on graph paper, then I would want to have a minus sign there. And the minus sign would stay, it wouldn't go away. It would be start here, and it would eventually show up out here in front. So in terms of Y coordinates, if the thing is, I didn't specify where the 0 point of the Y coordinates was, but if where Pippin was the 0 point of the Y axis, then the bottom would be at negative 50.8 or negative 50.18 meters. Okay, so does that answer your question? If you have a simple drop distance, all you care about is how many meters down you're going. You don't need the negative sign, so it just makes things a little easier. But if you're in a position, if your task is to compute a position or maybe a velocity, and like on a ballistic arc of a golf ball, you can compute the velocity at any point on the motion, and sometimes the velocity is going to be up, sometimes the velocity is going to be down on the second half of the motion, and then you're going to need a negative velocity, so then you want to use negative 9.8 for that kind of a calculation. All right? But if you know everything's positive, or if you just want to know how deep it is, you can keep things simple and use a positive number. Katia? Yeah, Dior, in this class, I'm going to always use 9.8. All right, just 2 decimal points for G. And the student here, Dior, was mentioning I always use 9.81, which you can do that. There are small variations from point to point. The top of Mount Everest, it is a little bit smaller, and relative to the surface, sea level. But 9.8 is still pretty good for pretty much everywhere, so that's what I stick with. Question?
Just to clarify, in different questions, is G always going to be like that specific?
Yeah, G is on the surface of the Earth. If we have any kind of free fall acceleration, free fall problem, so a baseball heading for the outfield, somebody jumping out of a plane, a Ferrari driving off a cliff, 9.8, and you might need to use negative 9.8 if you're doing coordinates or velocities. Question?
And how come we were really raised with 9.81?
I wasn't raised with 9.81. Okay. Well, the ground rules in here are use 9.8. Okay, so makes things a little simpler. All right, so your answer is 50.18 in depth. So now, as I mentioned, in position formulas, we might want to use negative 9.8 meters per second squared. And actually, we're going to do that because we're going to put a position formula together now using Galileo's various formulas. So here we go. And what we're going to do is we are going to think of a ballistic arc of a baseball. All right? And the baseball to the top of its arc, it's a parabola. It's a parabolic arc. All right? So this final height, or the final coordinate, is y subscript f. Okay? And down here at the starting level, the y coordinate anyways, it's y subscript I. Now that's its initial y coordinate. All right? So now, young lady in the back that was asking me, yo, it was you? Okay. Okay. What is your name? No, yeah, what is your name? Mia? All right, so Mia, now we're going to start thinking about the negatives. All right? Because we're thinking about y coordinates. All right, so you start at y subscript I, and you've got, this thing's obviously starting with some upward motion. It's on the way up. So it has some initial speed, all right? And the initial upward speed, now here's the distance rectangle formula, and the symbol V I subscript IY means initial speed y component, right? Now, it has some sideways velocity as well. Right now, we're not working on that right now. That would give us something about the x coordinate. But the y coordinate, we're just focusing on that, Mia. And, now, in this motion, Vi subscript y, or V subscript Iy, that's going to be a positive number. Because, go ahead and write that down. VIY is a positive number. Now, I'm not giving you the number. I don't even know what it is. But you know it's positive because it starts on the way up. It's moving upward. So this is like the first half of the motion. You know, the baseball player hits the ball towards the outfield. In other words, it's moving upward. Now, eventually, it's going to go over the top and start coming down to the outfield or maybe to the bleachers if it's a home run. But yeah, to start with, it's going to be a positive number. Now, it's also going to start slowing down because it's an accelerated system. That's where the 1/2 GT squared comes in. And this, Mia, and everybody, this G, if you do any computations here, yes, you want to use negative 9.8. All right? Question in the back? No? Just stretching? Okay. I saw a student just kind of faking me out like this, stretching. That's all right. But anybody else have a question here? So okay, go ahead.
Could you explain again why we're using negative 9.8?
Because it's considered a free fall equation, okay? And gravity is always downward. The acceleration of gravity is downward. If you're on the way down, you get more speed in the downward direction. If you are on the way up, you lose what you got until you have 0 at the very top. So up there, go ahead and make a note. At y subscript f, you're at the top of the motion, and the vertical component of the velocity, Vfy, is 0. Viy is, positive 16.2 meters per second or something. Whatever it happens to be. It's going to be a positive number. But at the top of the motion, you definitely know that you've lost all your... And that's because gravity is negatory in the vertical direction. It's vertical, and it's negatory. You lose it. If you've got some on the way up, you're going to lose it. And then you're going to start going on the way down, you're going to start falling again, and you're going to get faster and faster on the way down. You're going to get more downward speed. And so that's why, and because we're computing a coordinate here, y subscript f, we're using a minus sign. So we're not just saying, well, how high up does it go? If that's all we want to know, we could just use 9.8. But for this, we have to, if we're in a coordinate system, left and right, negative and positive, up and down, positive and negative. So you got to keep that minus sign in there. So this is a more specialized equation. Now let's look at this equation. Let me emphasize a couple things. If nothing happens to the baseball, the final y-coordinate is the same as the initial y-coordinate. All right, so that's your starting point. If it's moving, if it gets some upward motion, it's going to move upward. All right, so this is where the distance rectangle comes in. But now, if you were on a space station where there's no gravity, this would be the last part of your equation. So you just go straight out. You wouldn't. But because you're on the surface of the Earth, you have a negative, you have a downward acceleration due to gravity. So that's where the distance rectangle formula comes in. All right, so each part of this equation, the first term, the second term between the plus signs, and the last term, they each tell part of the tale of the dynamics or the motion of this baseball. Question?
Does the IY stand for like the distance?
IY stands for initial y component. So V subscript IY means the y component of the initial velocity, right? All right, now, Sir Isaac Newton and Galileo, they were all over this formula. Sir Isaac Newton was an interesting guy, and he thought a lot about things that are dropping out of the sky. The famous story about Sir Isaac Newton, the apple that fell out of the tree and conked him on his head, which nobody knows if that actually happens, if that actually happened to him, but some people say that it did. Maybe one day we'll find out for sure. But if you're, Galileo and Sir Isaac Newton, they were both thinking a lot about things falling off, falling. So Galileo thought a lot about motion on a level surface that ended abruptly, like at the edge of a cliff. All right, so we're going to talk about, now, there were no such thing as Ferraris in the day of Galileo. But we're going to think about, somebody that deliberately drives a Ferrari off a cliff. Like in a movie or something, how the stunt men, they drive. So, although I don't think this particular, that they wouldn't let a guy drive this far in a car because that'd probably kill somebody that far. But anyways, that's the other half of the motion. That's the downhill side of a ballistic arc. So that's the second half of a baseball. And the first half, though, is at the top of the cliff. So this is what happens to a Ferrari. It's on a horizontal surface, frictionless, but that stops. And once it goes over the edge, it starts following a ballistic track that a baseball would take. Okay? So if you rolled a baseball off the top of a cliff, it would follow a similar path. All right? But it's more fun to think about a Ferrari. All right? Now, this is where we start talking about Aristotle again in a serious manner. Because in Aristotle's view, every motion requires some kind of a mover or a force. Okay? If there's no force acting, it won't be in motion. It'll be at rest. All right? That's how Aristotle thought of motion. And up until the days of Galileo, that's how everybody thought. And it's not hard to see that. I mean, some people think that Aristotle, oh, what an idiot. But really, he was a smart guy. And it's not unusual to think, everything, because everything, if you're in the grocery store and you push a cart down the aisle, eventually it's going to come to a stop unless you keep pushing it. All right? And then if you leave it by itself, it'll come to a stop, and then if you don't do anything, it'll just stay there in the grocery store. So Aristotle wasn't, he wasn't like totally blind, but Galileo came up with a different view. And Galileo abstracted out all the forces except for gravity. He said there are forced motions, and he agreed with Aristotle about that. And he said there are unforced motions, in other words, no force acting, but they don't accelerate. And that is where he differed with Aristotle. So they neither slow down nor speed up. Now that's the flat surface at the top of the cliff. So that Ferrari, once it gets going at the top of the cliff, Galileo said up there, if there's no friction, that shopping cart will just keep on going. 2 meters per second, or whatever the speed is. And then as soon as it gets to the edge of the cliff, it'll retain that 2 meters per second horizontal, but then it'll acquire a forced motion due to the force of gravity. And so driving a Ferrari off a cliff from a horizontal, frictionless plane, the object, and this is the word that Galileo used, it's indifferent to being at rest or in motion. Up there on that hypothetical horizontal surface without friction, it doesn't care if it's in motion or if it's at rest. It doesn't need a force. It doesn't need a force to stay in motion at constant speed. All right? And it doesn't need a force to stay at rest. So it's indifferent. So in terms of forces, it's indifferent to those two states of motion. And if it's in motion, it will persist at constant velocity until it leaves the plane. And then it drives off the edge of the cliff. And then, you get this situation where you're on the way down. Just like the second half of a baseball, I don't even know how they did this stunt. This is like from a movie, right? Fast and Furious or something. It's kind of a cool photo. So now what Galileo did is he said, all right, Aristotle, you have this idea that every motion requires a mover. And if something's at rest, no forces on it. But if something's moving at constant speed, it's got to have at least a little bit of a push of some kind or a pull. All right? Now, here's how Galileo defeated Aristotle. All right? So the initial contention is, according to you and Aristotle, the object will move along the horizontal plane only if it experiences a certain amount of push force. So that's like Aristotle saying, all right, your hypothetical plane is like the aisle at the grocery store, all right, in Athens. All right, and if you push a cart down the grocery store in Athens, it'll come to a stop. So you got to keep pushing it to keep it going at 2 meters per second or whatever the speed is. All right, so here's the picture. Aristotle. You need a bit of push force here, and let's say that's 0.02 metric units of push force. So that's the symbol P to represent push force. And this is on a little car here. All right, and so Aristotle said, all right, you can have constant speed, no problem. You just got to have a little bit of a push force. All right, so let me put that up here, and go ahead and make a dot here to represent the center of mass of this car. So kind of in the middle there between the wheels. All right, now at that center of mass, the weight force is going to be acting. Now Galileo knew about that as well. All right, and that weight force, and and the push force that Aristotle is envisioning are contradictory. And I'll show you how they contradict each other. And so Galileo said, all right, here's the weight force. And he said, all right, very nice, Professor Aristotle. The car has, so many units of weight force. Let's say that it's 0.100 metric units of weight force. Now, I measured out these arrows, and they are in a ratio of 5:1. The weight force is 5 times longer than the push force arrow. Okay, it might not look like it, but it is. All right? And so Galileo said, look, take that, copy the push force, copy the weight force, and, change the weight force and the push force and make them into a right triangle like this. All right? So, in other words, a right triangle that is 1 unit in height and 5 units on the slant. All right? So that means take a 5-meter board and a 1-meter board, make the 1-meter board vertical, and then balance the 5-meter board to make a triangle with the floor. Right? So that's what this is. So there's your triangle. Right? So Galileo's thinking, remember, his conviction is Mother Nature works and expresses herself in terms of geometric figures and mathematical concepts. So we're looking at the geometric backbone of motion right now. So Galileo says, all right, you say a push force of 0.02, and if it has a weight force of 0.100, let me just take that ratio, 5:1, and make a ramp. All right? And you may say to yourself, Dr. B, what does the ramp have to do with anything? It's coming. If you put the car on the ramp, the component of the gravity force, the component of the weight force that pushes it down the ramp is exactly the same as the push force here. All right? So Galileo is saying, look, you say that you need push force, 0.02 units of push force. All right, I'll build a ramp that's 1 to 5. The weight force alone will be 0.02 units down the ramp. So if your ramp is, so when you're on a ramp, you don't get the full downward, acceleration, but you get some of it. The steeper the ramp, the more like if you're on a hill, the steeper the hill, the faster you slide down. So if you're on a ramp 1 to 5, you get this much right there from your weight force. All right? So Galileo said, look, Aristotle, you say that a flat plane requires 0.02 units of force to keep something going. But that's not right. Because a ramp, you need 0.0 units of force to either keep something stable on the ramp or to, so if you're pulling backwards up the ramp, it's got to be 0.02 because that's what gravity's given it naturally. So gravity will naturally accelerate it down the ramp. And to keep something at rest, you need 0.02 units of force to keep it at rest on the ramp. So what that means is, you, Aristotle, on the flat plane are overestimating because 0.02 units of force does the job on a ramp. A flat plane is going to need less than that. So no matter what Aristotle said, the flat plane is going to require less than any number that he can propose. So if Aristotle says, all right, well, let me dip it down to 0.01, well, Galileo can say, all right, I can build a ramp 1 to 5 instead of 2 to 5, or 1 to 10 instead of 1 to 5. It's no problem. It's still a ramp, and it's not flat. So then Aristotle, all right, well, 0.01 is too big. Let's go to 0.001. And so Galileo can say, dude, I got a ramp for that. Anytime you propose a force, I can build a ramp to contradict what you are saying. Therefore, on the flat plane, the state of motion exists, constant velocity, but without what Aristotle said. You don't need a push force. You need zero force. And that is what Galileo was able to prove. So Aristotle was up there in heaven probably saying, good job, Galileo, you did it. You got it. I didn't get it, but you got it. So no matter what, up there on the flat ramp, you need 0 units of force. Now, let's talk about something called the inertial state. And because this is related to Galileo's law of inertia, that an object without external forces will continue at rest or its state of motion at constant velocity in a straight line motion unless it's affected by an unbalanced external force. All right, so Galileo proved that there are 2 states of motion corresponding to no force, the state of rest and the state of inertial motion. So an object with no forces acting on it will stay in a state of motion that is constant speed, constant direction, unless something acts on it, some other force acts on it. And this actually became Sir Isaac Newton's first law of motion. Right? So now let's look in chapter 3 and start talking about Sir Isaac Newton and the laws of motion. Here's the first law of motion. Every object retains a state of rest, or the state of uniform straight line motion, unless acted upon by an unbalanced force. Now that's how Sir Isaac Newton phrased it, but the guy that figured it out was Galileo. And he showed that basically that what Aristotle was saying was contradictory. It took over 1,000 years, almost 2,000 years, for somebody to figure out a way to contradict Aristotle. Galileo was the guy that really started everything. So let's do an example of this. Let's take a look at it. An apple on an apple tree. Very common everyday example. So if the stem is attached to the branch, the stem is pulling upward. The gravity is pulling the apple downward, and the stem is pulling upward, and everything is fine until the stem weakens. And if the stem weakens, it can't provide enough force, and the balance fails, and down it falls. So it'll stay at rest if there's no force acting. Or if there's forces, they balance each other, like the stem and gravity. So if the stem dries out and gets brittle, it'll fall. And that's what happens every, fall, when fruit falls off the tree. Now, here's another application of Newton's first law, the law of inertia. Think about a bus, and this is mentioned in the textbook as well. If the bus moves forward, you're standing out in the aisle, the bus moves forward, you're going to lurch backwards. You're going to go, whoa. It's going to be as if you're, and the reason for that is you are not stapled down to the bus. You're not bolted in. The seats go wherever the bus does. The wheels go wherever the bus goes. The windows go wherever the bus goes. But you, if the bus goes forward, you're going to want to stay where you were. So you kind of topple backwards a little bit. If the bus goes to the right, you bump your left hip. You know, because you're going to try to keep going straight. Because you're not bolted into the bus. So your natural tendency is to go straight, even though the rest of the bus is going off to the right. So it's going to be as if you're thrown to the left. All right? So that's why on a bus, you stabilize yourself fore and aft, port and starboard, unless your bus never changes its motion, its state of motion. But that is not possible. The buses that I've ridden here at UCF, oh my goodness, they're always bumping and it's really a rough ride. Okay, let's dismiss. Homework will be ready by lunchtime tomorrow. Go ahead and dismiss yourselves, and I'll see you guys next week.